Okay. So I told you before, today's class we're going to learn the first model in the process. Okay. So already I told you we have discussed this. Probably ma'am also would have discussed with you. See, the way we make the PN junction is generally involves two steps. One is the pre-deposition step. Second is the annealing step. You heat them, right? So there are two steps, and these are the three common ways to form the PN junction. This just I'm referencing you to know the context, because see, in all the three, the diffusion mechanism will happen, because we're going to see today the model for the diffusion mechanism. So it's good to know the diffusion first, then we go and form the equations. I hope some of you can able to guess the equation before we actually see the complete one. Okay, so even here, so hope you guys able to remember, right? We take a piece of silicon, and then what we do, you guys remember this, right? We take a piece of silicon like this, and blue color thing is your silicon wafer, something like this. I'm holding my hand, and you'll be treating the gas here, right? And that's a pre-deposition step. And the second step is when you heat them. When you heat them, this dopant start entering into it through the mechanism called diffusion. Okay. So have you heard of diffusion before? Anyone already know diffusion? So that's what. So diffusion is what going to see. We're going to see today. Now we have seen already. So I'm just going for this. I think this is all we have seen already. Okay. So we're going to see modeling of diffusion. Okay. So before that, we should know what is diffusion. So why we need to model first? Anything? Why we need to model? Why we need to? What is model? What do you mean by modeling? Guys, what do you mean by modeling? It's forming, expressing anything in exactly mathematical form, right? So by doing that, we understand them better. Okay. That's why we suggest you can see this red one, the accurate control of the placement of active doping region. That means we understand them better, so we control the process better. We know what is the driving parameter, so we can control the entire process better. That's the one advantage of the modeling. Okay, so we understand them and we control the process, and that's why we're going to learn the modeling part. Okay, not only that, this model helps us to do your computer simulations rather doing your hands-on fabrication. You can do your simulation first before you do the actual fabrication. Okay, so that's why this model is also useful. And today model is going to be like the starting point for the advanced models. So that's very important. Okay. So in the modeling, we have two types. We're going to study both. One is macroscopic model. We model the end effects. Other thing is microscopic model. We go to the details to the atomic level. So atomic level modeling, as well as that's also called microscopic modeling and macroscopic model. So today we're going to learn macroscopic model. What is the effect, the final effect? Okay. So we predict the overall motion of the dopant profile. Right. That's what we're going to see in today's class. Okay? So don't worry about it. We'll see. Okay. We'll learn. We will once you start learning the model, you understand this better. Okay. We'll come to this again. Don't worry. We'll come to this macroscopic model again. Okay. Now I want to, because we're going to model the diffusion mechanism. Let us learn the diffusion first. Okay. So able to see this one, right? So what do you understand from this one? The left one. After some time, it does. So after some time, it has become like this. So what do you understand from this? What has happened here? Anyone? This mechanism is diffusion. What has happened here? You want to say something?
It is going to lower the concentration or higher concentration.
Yeah, it is spreading, right? It is. See, it's actually at one place and it started spreading evenly, right? See, also you can see here. If you have an ink here, so what will happen after over the time? Over the time, what has happened? Over the time, they started spreading. What is their driving force? What causes the movement? What causes the movement for that blue molecule to spread? What is the driving force? What has caused the movement? Someone is pushing that? No, right? No one is pushing there. What is the driving force for that to happen? Anyone able to visualize what is the driving force? What has caused the movement? It is moving, right? That's why it is spreading. What is the driving force behind that movement? Or even you can take other example, same one, but one thing you have to note here, when it is hot, it spreads better. Okay, please note this one. When something is hot, it spreads even faster. Okay, please note this. Maybe you can note it in a notebook. And then you can see here, so we have seen diffusion in the solid. Suppose you spray a perfume at one part of the room. The person at the other end can smell the perfume, right? What is the mechanism? What has happened here? So you spray the perfume in one part of the room, but the other part of the room you can smell that same perfume, right? What has happened? It is diffusion because it is the movement of molecules from one place to another. Now the question is, what is the driving force? Then only we can model it. What is causing the movement? Okay, we observe there is movement, but what is causing the movement? So this one fragrance, the same diffusion. So you have seen in liquid, we have seen in gas, and we also observe diffusion in solids. That's what going to be in today's focus. Similar mechanism. So you can see here, you can see lot of blue atoms which has started entering into your solid. This is what happening in your doping process. You have a wafer, that's your solid thing, it could be silicon, and this dopant, they start entering through this mechanism. Okay, so you can also see here from this animation from Wikipedia, see once these barriers are removed, this molecule started moving naturally. It's a natural happening. It's a spontaneous process. No need to apply any voltage or temperature gradient, not required. It's a natural process. So I want everyone to note, diffusion is a natural mechanism. It's a spontaneous mechanism in your book. And it increases with temperature. And diffusion happens faster at higher temperature. Two things you should note. Okay. Now I want everyone to think, what is the driving force? What was causing it? Then only we can model it. Anyone, any guesses? What is causing the movement? We are not applying voltage. It's not because of voltage. We are not having any temperature gradient. What is causing the movement? Hope you have written. Hope you can move to it. Next one. So now we're going to discuss the model for this mechanism. Okay, we all see diffusion, right? Diffusion is what? You put something in one place, it started spreading naturally, spontaneously, right? So that is diffusion. Now we're going to see how to model them. To model them, we should know what is causing the diffusion mechanism, right? So the reason for the diffusion mechanism is it's a difference in the concentration. See, if you spray a perfume here, the perfume is there are more amount of gas molecules here. And other part of the room, there is no molecule. So because of this difference in the concentration, they move. So the driving force is just difference in the concentration, nothing else. You don't need to blow air, you don't need to increase the temperature, nothing. It naturally happens, just the difference in the concentration, which mathematically called as, can you able to guess? Mathematically, you would have heard of this term. Whenever you have a difference in concentration with respect to space, what you can call it as mathematically? Anyone in the hall? This called gradient. Have you heard of this word mathematically? Gradient. Gradient is what? Difference in concentration over the distance. It's called gradient. So the driving force is concentration gradient. I want everyone to note this point. What is the driving force? It's a concentration gradient. Okay. So slowly we are moving to mathematical part. We are going to model. See, we learned the concept. Now we're going to model it. So I want you to try this. Okay. So please, how do you write mathematically gradient? Concentration gradient, how do you write mathematically? Guys, how do you write mathematically the gradient? Anyone? You can be wrong. See, you can just feel free to answer even wrong answers. Just I want your interactions. How do you write gradient mathematically? Anyone? See, you have a, I told you the driving force is concentration difference with respect to distance, right? So how you can write this one mathematically? You assume the y-axis is concentration and x-axis is the distance. Okay, y-axis is concentration, x-axis is difference. You assume there's a large. Let me draw here. This is your concentration. Okay, this is your distance. Okay, depth. What I mean depth is your wafer. You are going downward. This depth. You have a concentration that surface. This is the top. This portion is top surface. Very difficult to write the mouse, but anyway, it's a top surface. It's a bottom, right? It's bottom here. You have a top surface. Now, now what I'm saying is what is the driving force? The constant is because you have a lot of dopants here. You have no dopants here. This difference in the concentration is going to cause the movement of the dopant into the wafer. Okay, the difference in the concentration is going to cause the movement into the wafer. So how do you say mathematically? It's constant gradient. How do you represent mathematically now?
Slope of that.
Exactly. Please give a claps to him. Please give that's a correct one. It's nothing but what? It's a slope. How do you write mathematically? dc by dx or dou c by dou x. That's going to give, because that's the difference. What is dou c by dou x? C1 minus C2 by, or C2 minus C1 by X2 minus X1. That's the difference in concentration with respect to the distance. So that is the driving force. So what is the driving force of the movement? The gradient, concentration gradient. So that's going to be called as Fick's first law of diffusion. The diffusion of dopant atoms depends on concentration gradient. Make sense? That's a Fick's first law and very important law. Right? That's your first process model. We slowly started modeling things now. Okay, we model the gradient. That is dou c by dou x. Gradient is what? Dou c by dou x. That's your slope, and that tells you how much difference in the concentration is, and that is the driving force for the diffusion. What will be the left hand side? What do you say for the movement? So let me show you that. Yes. It's not so better audible, but anyway, it's called flux. It's called flux. Flux is nothing but, guys, see, listen carefully. What is flux? This term we'll be using frequently. So listen carefully. What is flux is very simple. The flux is, you have a bunch of atoms, the number of atoms crossing per unit area per unit second. Number of atoms or dopant atoms crossing per unit area, crossing this per unit area. Crossing this per unit area per second. Okay, now tell me what is the flux for this one? Assume the unit area is 1 here, 1 centimeter square. And see, guys, in semiconductors, the dimension unit is always centimeters. Okay, we will be using centimeters. In TCAD, it is micrometers. For theory, we will be using centimeters. Okay. So whenever I say per unit area, it means per centimeter square. Okay, per second. And anyone can tell me what is the flux here? What is the flux of this one? What is flux definition? Number of atoms crossing per unit area per second. What is the flux here? 3. Exactly. That's a flux. And can you please think about what is the unit of the flux? What is the unit for the flux? Number of atoms per centimeter square per second. Atoms per centimeter square per second. Yes, centimeter power minus 2, yes minus. Right? For number, we don't have unit. That's a number, right? So just the unit is centimeter power minus 2 per second. Okay. So now, can you get mathematically now? See, you got, so the flux is what number of atoms moving in. That is your, so that depends on what? Your concentration gradient. Can you write it as a mathematical form? Mathematical form. They are dependent. We have more gradient, then the more number of atoms enter. How to write mathematically? You have to relate them. How to relate them? Guys, how do you relate them? Exactly, directly proportional. So for flux, give me some variable. It's F, right? So F directly proportional to what? F directly proportional to, yeah, what is dc by dx? Exactly, right? So please write them by F directly proportional to dc by dx. Written, everyone? Now let me give you a small sample instance. Sorry, I don't have a board here. Assume this is the concentration, this is distance, the concentration gradient, something like this, right? Now tell me, if you take the gradient for this, what is the value will come? Which from this, can you guess what is the what will be the what is the direction of the flux here? The flux, the dopant atoms are moving from left to right or right to left? Dopants always move from where to where? Higher concentration to lower concentration. So which side, where is the higher concentration here? Left or right? So where is the movement? How the dopant will move? Going to be left to right or right to left?
Left to right.
Exactly. So dopant movement is going to be left to right because there is a higher concentration here, lower concentration here, other side, right side. So the dopant is going to move from left to right. Right. Now if you take dc by dx, what is the value you will get? For this one, for this line, if you take the gradient dc by dx, what is the value you get? Whether you any idea about the slope here? What you can say about the slope? For this decreasing line, what you can say about the slope? What is slope? C2 minus C1 by X2 minus X1. So from this, what you can say? Guys, following? What you can say? The slope is positive or negative? Negative. And if you have negative, so flux will be negative. Negative means which direction it will come far? Negative is this left to right or right to left is negative? Yeah, right to left is negative, but the flux is what direction? Left to right. So there is a problem here. Now, how do you compensate that? So you understand that the constant gradient gives you negative value. Actually, the flux is from left to right, right? For our case. But the gradient gives me a negative value. Negative value means it means the flux will be moving from right to left. Now, how to compensate that? How to overcome that? But flux is moving from left to right. What we can do now? Hope you have not seen the screen, right? I have the board. I would have. What do you have to do? Guys, you can be wrong. Just if you don't understand, also ask me to repeat. Okay, just. Guys, already we have what equation? F proportional to dc by dx. Correct. That is the equation we have. But what is the problem with that equation? dc by dx is giving me negative value, which means it tells me the flux is flowing in the wrong direction. That is not correct. How do I change the direction now? Huh? Adding a? I'm sorry, guys. It's not much audible to me.
Multiply by negative sign.
Exactly. Multiply by negative sign. That's it. So F is proportional to minus dc by dx because of this. Guys, please try to understand. It's very simple. If you understand, it's better. Okay. If someone didn't understand, please ask me. This is very, very important. Why that is minus? Minus tells you that we are adding an extra minus because to correct the direction of the dopant atoms. Okay. The constant difference is a driving force, but if you use the gradient, that gives you the wrong direction. To compensate for that, we add an extra minus. Okay, all fine. But now, how do you remove the proportionality sign? Proportionality constant, exactly. So the proportionality constant is called diffusion coefficient, and that gives you the fixed first law. So F equal to minus d by d into dou c by dou x. So that is the first law of diffusion. So where d means diffusion coefficient or diffusivity. Okay. So what is diffusivity means? How freely the dopant atom can move in the silicon. Okay. If it is germanium, diffusivity will change. If it is gallium arsenide, it's a different material, diffusivity will change. So diffusivity is a material property. So diffusivity tells you how freely the dopant atom, foreign element, can move in the wafer, can move in your substrate. Make sense? Please note this. What is diffusivity? Please write. Diffusivity is how freely the dopant atom can move inside your substrate or wafer, whatever it is. And guys, I always prefer you write, understand and write on your own words. That's very, very important for your understanding, for a better understanding. And writing is also part of the learning. Even though I'm recording it, it's better to write because you grasp it better. Okay, any doubts here? Fix first law. Okay, can someone find the unit for diffusivity? What is the unit of diffusivity? Flux, we know the unit. Concentration, what is the unit? What is the unit for concentration? What is the unit of concentration? When I say concentration, what I mean is, I assume 1 centimeter cube volume, a cube. I assume a 1 centimeter cube, okay, or volume of 1 centimeter cube. And in that, how much number of atoms are there? That is what concentration is. So that's why unit is always centimeter power minus 3. In a box of 1 centimeter size cube, how many number of atoms, electrons or holes are there? Okay, so depending on what you refer. Here we refer the dopant concentration. So we refer the dopants. So unit is always centimeter power minus 3. What is dx unit? What about x unit? What about x unit? What is unit of x? Centimeters. Now substitute all and tell me what is the unit of d? Diffusivity. Quick. We have a small problem to solve as well. Oh. Okay, done. Anyone found what is the unit of diffusivity?
Meter square per second.
Yeah, very good. Centimeter square per second. Very good. So that's the unit of diffusivity. And now you can see here. See, actual concentration will be something like this. We'll be learning about them. Don't worry. The profile. Can you give some name for this profile? Any guesses? How it looks like? See, if it is like this, the profile is. What is the name for this curve? Yes, what is the name for this one? It's a line, right? Maybe my drawing is poor, but it's a line. It's a line profile, right? And suppose if the profile is something like this. What is the name for this profile, So what is one? What is this one? This is exponential, right? This is exponential. That's how your IV characteristic of diode looks like, right? This is line
Sir, the diagram
exponential.
is not
So for this
visible.
one, what is the name? What is the profile for this one?
Sir, the diagram is not visible.
Sorry?
Whatever you are drawing is not visible here, sir.
Oh, okay. I'm sorry. Why it is though? Let me present start again. Sorry. Thank you. Thanks for everything. Now it's visible? Now it's visible, pa?
It is visible, sir.
Yeah, thank you. So this is your line profile. Okay, this is your exponential profile. Now I'm asking, what is this profile is? Any guesses? It is called Bell because it's like we'll see later. It's called Bell profile or otherwise called Gaussian profile. We come to it later. So this is the profile of concentration, this distance. Now over the time, what will happen? Pa? Now just I want you to draw. After some time, what happened to the profile? After some time, what will happen? This is the initial profile at time t1. After some time, what will happen to the profile? What will happen to the dopant atoms? Guys, draw this curve and the same graph, try to draw after some time, what will happen to the dopant atoms? What will happen, Pa? Any guesses? I mean, we already know, right? What will happen? The dopants are will start moving inside. Okay, so what will happen to the profile now? Just try drawing in your notebook. Just drawing in notebook, then I will disclose here. Just remember, it is your initial profile at time t1. Okay, the dopant atoms are distributed like this. After some time, what will happen to the dopant atom? We know from the fixed law of diffusion, the dopant will start moving deeper inside. So what will happen to the profile? So if they move deeper, what will happen to the profile? It will go even deeper, right? You will have more dopant getting inside the wafer because X is your distance. And what will happen to the concentration here? Suppose you have 100 dopants here. Assume 30 dopants have entered after some 5 seconds or 10 seconds. So what will happen to the concentration here? Is following? See, assume there are 100 dopants here at this point. After some 100 seconds or so, assume this some 30 dopant atoms have got into the wafer. And what will be here the concentration now? Not clear? Guys, we have 100 atoms. 30 has gone in after some time. So how much will be? 70 will be, right? So what will happen to the concentration? It will decrease in the surface and the concentration increase in the depth. Able to follow? This is your depth, right? I told you this is depth. That's what we are drawing as 1D profile in this direction, horizontally. So depth actually, so dopant atoms are coming in. So over the time, they move deeper inside. The concentration will decrease in the surface and they go even deeper. Can you able to draw that? So it will be something like this. See? What has happened here? It has gone deeper and the surface, the concentration has reduced. This movement is governed by fixed first law of diffusion. Okay. Does it make sense? Anyone doubts in this? Shall we move to the next one? Okay, if no doubts, we can move to the next one. So y negatives I told you, units I told you. Now let's apply. Okay, so this is your X. It is the depth inside your wafer, your silicon substrate. The y-axis is your dopant concentration. Assume the profile is something like this, and you have to find the flux. Okay, so find the flux for this problem. What do you need to find the flux? Assume this is your zero, this is your top surface. So assume this is your x is zero here. Okay. So F equal to what you will find? Do you need any other parameters here? Yes, please note down this problem and tell me, do you need any parameters to find the flux? Do you have all the parameters?
Sir, do we need time?
Time? No. See, look at the fixed law. Do we have any time parameter there? Time comes in the fixed second law. So, but anyway, that's a good guess you made. Not the time here. Yeah, someone is saying. What is that? Diffusivity. We have to find the flux. What is flux equation we have seen? F equal to minus d dou c by dou x. We have c and x. You can find what? You can find the slope. What is missing? Diffusivity is missing. So assume diffusivity is 10 power minus 15. You know the unit. Already you calculated the unit. So it's going to be centimeter square per second. So please write that and find the flux. Let me see who will answer first. See, dc by dx, you know how to find, right? This is your C2. This is your C1. So C2 minus C1 by X2 minus X1. Okay, that's what you have to find dc by dx. Quickly find and let me know what is the value for the flux you got. You don't need a calculator here. Very simple. What is C2 bar? What is C2? Guys, what is the concentration here? See, what is the concentration here? It's not clear how to find. See, dc by dx is C2 minus C1 by X2 minus X1. Okay, my question is, what is C2 here? Okay, what is C1? Guys, please interact. It's very difficult with online class. Okay, this is C2, right? What is C2 here? What is the value of C2? What is given the concentration here for C2? What is the concentration here? 10 power 10. So C2 is 10 power 10 minus 10 power 15 divided by X2 is what? 1 micrometer minus 0 micrometers. That is dc by dx. So what is 10 power 10 minus 10 power 15? Anyone knows the answer? 10 power 10 minus 10 power 15 is? Don't use the calculator. You can tell just like that. Anyone? 10 power 10 minus 10 power 15. What is the answer? Guys, please respond. See, my question is clear or not clear? 10 power 10 minus 10 power 15. What is the answer? Ma'am, am I audible? No, ma'am. Jayanti, ma'am.
Yes, sir, audible. Actually, students are working out. Yes,
Oh, okay.
audible, sir. Yeah,
Okay, ma'am. Thank
they are all working, sir. Yes.
you. Thank you. Please, but there is nothing to work here. Why? Because see, 10 power 10 is, see, like, oh, okay, let me give you another example. 0.1 minus or 0.001 minus 0.1. What is what you get? Or 1. 0.0001 minus 0.1. What do you get? Question is clear, not clear? 0.0001 minus 0.1. See, this very small number not going to make any difference. So it's again going to be what? Minus 0.1 only. Similarly, 10 power 10.
Answer is 10.
10. 10 power 10 minus 10 power 15 is 10. Are you saying the final answer?
Yes, sir.
You're saying dc by dx.
Final answer after calculating it.
Divisivity also. Okay.
So,
Yes.
is the answer 10 past 7 for the
Let me check what. 10 power?
7?
10 power 7. Okay. I got 10 and 10 power 7. And any other answers?
Ten power 6 and
10 power 6. Okay. Okay, let me try to type it here. See, dc by dx is what power? C2 minus C1 by x2 minus x1. So what you will get is 10 power 10 minus 10 power 15 divided by 10 power minus 4. Why minus 4? It should be minus 6, right? Micrometers means minus 6. But our unit is centimeters. So you have to convert the micrometer to centimeters. So how much? How would you convert micrometer to centimeter? Micrometer is 10 power minus 6. Centimeter is 10 power minus 2. So to convert micrometer to centimeter, you have to multiply 10 power minus 4. So 10 power minus 4 centimeters. So I made, see guys, this is very important step. For some of your seniors have made mistake in this. So because the denominator is micrometer, numerator is centimeter, so you have to convert to same unit. That's very important. Otherwise you make mistakes. So what you will get here is the numerator is again what? Just 10 power 10 minus 10 power 15 is 10 power 15 only. You can check in the calculator also. It does not make much difference. Because the 10 power 10 is a very small number. So you'll be getting minus 10 power 19. Okay, the unit is centimeter power minus 4. Now, if you calculate the flux is what? Minus divisivity, which is 10 power minus 15 times 10 power 19. So the answer is, here also we have minus. So minus becomes plus. That's why we add the minus there, right? Previously. So 10 power 4 is the flux. Centimeter power minus 2 per second. So what it means? Per second, per centimeter square, 10,000 atoms are entering into the wafer. That's what it means. Any doubts? Anyone has any difficulty mathematically here? Fine for all? Or maybe you have done already, you can repeat the problem for this one. You can assume x naught equal to 0.5 micrometer and you can take this as your homework as well. Okay. And now my question is, if divisivity is 10 power minus 10, what will happen, Pa? What would have happened? The flux will increase or decrease? Just qualitatively tell me. If you diffusivity here for this example is 10 power minus 15. If it has become 10 power minus 10, what could have happened to the flux? Will increase or decrease?
Increase, sir.
Sorry?
Increase.
Exactly. Because you're increasing the diffusivity. 10 power minus 15, guys, it is minus 15. So 10 power minus 10 is you're going smaller, right? Sorry, you are increasing. 10 power minus 10 is It's a bigger number compared to minus 15. Because diffusivity increases, your flux depends directly on diffusivity, your flux increases. Okay. And also, if you decrease the x naught, what will happen? X naught, if you decrease, what will happen? The gradient will increase, the slope will increase. Since the slope is increasing, the flux again will increase. Okay, so you can check that. So you can have a qualitative understanding, and then you can find the right math afterwards. Okay. Fine for all. Shall we move next? Or any doubts still existing among yourself? Okay, so could be some silly mistakes or silly doubts. Even please speak out. They are your friends. If you don't understand, please shoot out your questions. No questions, then we can move again. Shall we move again? Hey, this to repeat the problem, you take as a homework. Okay, sorry, homework. See, probably when you come for next Monday, there will be a quiz for you, pa. Okay, so please be prepared for that. So I told you, like every week we plan, but last week we were not able to do. But from coming Monday, it will be happening. So coming Monday, please be prepared for the quiz and come. Okay. So whatever we thought, that will be there. Okay, based on that. Okay, so I think I can move. If no doubts, I can move forward. So see, guys, this fixed form. See this fixed equation. This fixed model, it was actually done in 1855. Very old. Okay, 1855. It was a German physician. He actually is a medical doctor who formed this model. Is not a what? A physicist. He's a physician, a medical doctor observing the biologically how salts and water are moving in the body. Right? It's a physician. Actually, he was at University of Zurich, Switzerland. Okay, during this thing, and he published this one at his 26 years. He was in 26. Okay, and the advanced model we're going to see that going to start with this wonderful fixed power diffusion. This simple model F equal to minus d dou c by dou x going to be the fundamental building block for the advanced models. Okay, that we're going to see. And this is also another important paper. This is actually a research article by Loney and Larabe. So what they did here is they are the first one to employ the fixed law, 100 years old, to the modern problem. This is very, very interesting. See here, fixed law is very old, right? 19th century, but they are able to apply it in 20th century. 100 years, almost 120, 130 years later, they apply the fixed law for the advanced model. Like they are studying the diffusion mechanism in the wafer. So they apply that here. Okay, so this is one of the interesting paper, and you can also see the similarity of fixed law with the other laws. Say for example, I'm not sure you have studied this one, but it is called diffusion equation in semiconductor devices. See, this will be coming back again in your unit 3, but I just want to link you. Don't worry what is happening here, but see the similarity of the equation. You have left hand term minus some factor into the gradient. Same form you can observe here. This again will be coming back in third unit. Okay, the equation is having the same form, similar expression. Okay, guys, don't get diverted, be focused here. Okay, and then another expression is this one. Okay, so this is your drift equation. This is called diffusion equation, drift equation. Again, you can see similar form. Left hand side equal to minus some factor into the gradient term. Okay, so this form is prevalent in semiconductors. Not only in semiconductors, it's also prevalent in other domains like mechanical. Those the heat flow. You can see similar form. A parameter, left hand side term equal to minus some parameter into gradient. This Fourier law of heat transfer tells you with difference in temperature how the carriers move. Guys, this you'll be learning in packaging. You study packaging course in your final year. The similar Fourier law, which is having similar as fixed law, you'll be studying. See, fixed law we are studying. We are using we're making use of fixed law to study the front end. A similar equation was explained in the back end also. You understand how mathematics is beautiful here. Similar mathematical expression explain the front end as well as the back end mechanisms. Okay, because heat transport is one of your back end technology. How do you going to take the heat out of your chip? That is governed by Fourier law, which is very similar to Fick's law. Okay, and then you can also see Newton's law of viscous fluid flow, which also follows the similar form. Okay, so I think we can stop here. So what we learned today is the very first step towards the modeling. And what we have seen is the dopant movement. The flux depends on constant and gradient, which can be written mathematically as F equal to minus d dou c by dou x. And this form is prevalent not only in semiconductors, but also in mechanical and other streams as well. Okay. So with that, we close here. Please do the homework problems. Thank you. And thank you very much, ma'am, for making this happen.
Thank you, sir. Thank you for joining with us.
Thank you, ma'am. Thank you.
Thank you, sir.